In this lesson, I'll quickly review what we've already learned about light. Light is generated from light sources. The most obvious one for us is the sun. So the sun is a star, and stars are giant clouds of hydrogen gas and helium gas, and the temperatures and pressures are so great in the core of the star that hydrogen is smashed together with other hydrogens to form helium, and that process of nuclear fusion produces light. So stars are a light source. The light we're most accustomed to is reflected light. So here on Earth, when we look outside, the sun's rays are hitting the rocks and reflecting off the rocks into our eyes, and so we see the landscape. The moon, we can see the moon because the sun's light is reflecting off the surface of the moon into our eyes. We're familiar that chemical processes can produce light. Flame has heat and light. Fireworks, again, heat and light. And of course, electrical devices produce light, so light bulbs. This is Las Vegas from an airplane. In a picture like this, then, we have both. We have light sources and reflected light at play. So the stars are light sources. In addition, this is an electric light bulb down here. And we see the foreground in the picture as reflected light from a flashlight. We learned that scientists think of light as a wave. Much like the ocean waves carry energy, light is carrying energy as well. And the waves that make up light are electric waves and magnetic waves. So we can think of light as an electromagnetic wave. The oscillations, the changing electric fields are generating magnetic fields, and the changing magnetic fields are generating electric fields. And this disturbance moves through space very quickly at the speed of light. We've also learned that visible light, all the colors of the spectrum here that we can see, is just a tiny fraction of the entire electromagnetic spectrum. And we can think of these waves as having different wavelengths. So a wavelength would be the distance from the crest of one wave to the crest of another. Just as in a water wave, the distance between the wave here and the one next door. So that would be the wavelength. And we see on the right side of the diagram are the kinds of electromagnetic radiation that have long wavelengths. Radio waves have the longest wavelength, and then infrared, a little bit shorter, and then the visible light spectrum here, ultraviolet, even shorter wavelengths. X-rays, gamma rays have the shortest wavelength, indicated by a smaller distance between the crests of the wave. And here now we'll add the actual wavelengths of the light. So radio waves can be a centimeter to 100 meters long, the distance between a crest and a crest. Whereas infrared, 1,000 nanometers to 1/100th of a centimeter, and ultraviolet light, again on the order of nanometers, and then we get gamma rays, really short wavelengths. But visible light has different wavelengths measured in nanometers, a billionth of a meter. We can also describe the electromagnetic radiation with a different term called frequency. And frequency would be the number of cycles per second, or the number of waves that move across a point in a given second. So of course, if the light has a shorter wavelength, more of those waves will travel across some given point in a second. Remember, light travels at the speed of light, and it's a constant. So if the wavelength is short, more of those waves will cross a point in a given amount of time. So the gamma rays will have high frequency waves, and the radio waves will have the lowest frequency of waves. And again, the visible light spectrum also has different frequencies then. So the purple light will have the shortest wavelength, and so the highest frequency. And the red light will have the longer wavelength, and so lower frequency. And this concept of frequency then is sometimes used to describe the energy of the wave. So high frequency light carries more energy than lower frequency electromagnetic radiation. So here's a summary then. If we just apply it to the visible part of the spectrum, The blue and the purple light here is higher frequency, higher energy, shorter wavelength. And the red, orange part of the spectrum, lower frequency, lower energy, and longer wavelength. Now, scientists have developed different instruments to detect electromagnetic radiation at different wavelengths. And so this is an important part of our study of the universe. There's a lot of the universe out there that we can't see because objects are emitting radiation of wavelengths that we cannot detect with our eyes.